Morning, everyone. I request Himanshu sir to start the session.
Good morning, sir. Okay. In the last class, we have discussed about the preparation of alkenes and physical properties, chemical properties. And the last we have done is oxidation. So basically, we have divided the oxidation into three categories: complete oxidation,
Sir,
incomplete.
your voice is very feeble, sir.
I'm not audible. Hello. Hello. So is this clear now? Anyone? Am I audible?
So it's very low, sir. Your voice is very low and feeble.
Hello. Hello. Is it still like this? Anyone else? Bhavna, am I audible?
Yes, sir.
Clear?
So can you repeat once again?
My voice is breaking or am I clear?
So you are clear, sir.
Okay. So maybe there's a network issue just because everything is okay from my side.
Yes, sir.
Okay. So, so we were discussing about the oxidation and oxidation was of three type: complete oxidation, incomplete and catalytic. Incomplete was in the, you can say, less amount of oxygen, less amount of carbon is present. And if I talk about the catalytic oxidation, we were discussing about copper tube and MO2O3, two catalysts we were taking. And now we have to discuss the fourth type. The fourth type is aromatization. The fourth type is aromatization. See, we know what is aromatic compound, those compounds which were following the Huckel rule. So now what we are doing, we are making the compound in such a way that they are following the Huckel rule. Okay, so generally we'll say that alkanes containing 6 to 8 carbon, 6 to 8 carbon, when they are heated,
Sir,
condition is,
sorry to interrupt, sir,
yes,
but your voice is very low.
I don't know what is happening. Let's start saying that
Eh,
I'm audible.
Students, are you able to hear?
No, sir. Sir.
Okay, I'll join it again. Wait.
So else you can join through mobile and speak through mobile, sir.
Am I audible now?
Perfect, sir. It's perfect now.
It's perfect now? Yeah.
Yeah,
Okay. So make me co-host.
done, sir.
Okay. So we were discussing the new type, that is aromatization. So in aromatization, alkanes at least having 6 to 8 carbon. When they are heated above the temperature around, the temperature at which heated, that is 773 Kelvin. When we start heating and the pressure we use is 20 atm. 20 atm, and generally the catalyst we use in this reaction is maybe chromium, it can be vanadium and molybdenum. Okay, so and the supporter on which the reaction occur, that is, you can say, alumina, supported by alumina. Can anyone tell me what is the formula of alumina? Al2O3. Okay, alumina is Al2O3, and aluminum oxide, just Al2O3, is amphoteric in nature. Just tell me what is amphoteric. What is amphoteric? Anyone know? Okay, amphoteric are those compounds which act like both acid or base. So it means if it is reacting with the base, it will act like acid. If it is reacting with acid, it will behave like base. Okay, so let's see a reaction. For example, I have hexane, N-hexane. Okay, I'm writing it like this: CH3, CH2, 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 CH3. So this is hexane, 6 carbon is present. So N-hexane, when heated in the presence of Cr2O3, chromic oxide, V2O5, vanadium pentoxide, or you can say MO2O2, molybdenum oxide, at Al2O3. This is the supported on which the catalyst is present. Okay, at the temperature I told, that is 773 Kelvin, and the pressure you have to take around 10 to 20 atm. Okay, so now what will happen? The process, we call it as cyclization occur. The process cyclization occur, and in the process of cyclization, what happen? There is a removal of H2. One hydrogen from here, one hydrogen from here. They will get eliminated, and now it will form a ring-like structure that is called cyclohexane. See, if one hydrogen will go from this carbon, and from that carbon one hydrogen is lost, each carbon have one valency left which is not shared with anyone. So they make a bond between them and cyclic structure is formed. And what you will do on dehydrogenation, the dehydrogenation means removal of hydrogen, minus 3H2. From every position hydrogen is removed, and it will form a aromatic structure. This is known as benzene. So the reaction was aromatization. So in this particular reaction, what we have done, first we have to heat the compound at 10 to 20 atm in the presence of Cr2O3, V2O5 over the alumina. Okay, so what happens? Cyclization occur, and when the cyclic product is undergoing that dehydrogenation process, it will eliminate out the hydrogen molecule. It will eliminate hydrogen molecule, and the compound we get at the last is a aromatic. Just because you can apply here that Huckel rule, and you'll see the n value will be the integer. So if the n value is integer, we have already discussed in the last chapters that it will be a aromatic compound. Okay, so one more example we can see. You have to tell me the answer. CH3, CH2, 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 CH2 over CH3. So this is a N-heptane compound. Again, same condition I'm writing: Cr2O3, V2O5, MO, MO2O3
over Al2O3. Temperature was 773 Kelvin, 10 to 20 atm pressure was there, and again cyclization occur. It means minus H2. Position will be same from here and here. One hydrogen will be removed. Okay, the product formed will be, see, I'll make the cyclic one only. You will tell me the name of the product here. This is called methyl cyclohexane. When it is dehydrogenated, it means minus 3H2. The compound formed will be, what is the name of this compound?
Phenol. Phenol.
Phenol. Phenol is when we have OH over this benzene. We have CH3 here. What we call this compound? Yes, anyone? See, it is toluene. It is known as what? Toluene. Benzene with OH is called phenol. Benzene with CH3 is toluene. And what is benzene with NH2? Benzene with NH2 is aniline. See, revise the aromatic class. Okay, so this was the aromatization reaction. Now let's discuss about the isomerization. This is the, I think, third or fourth type, whatever it is, isomerization. See, what happened when N-alkanes, are heated, when N-alkanes are heated with anhydrous aluminum chloride and HCl. Temperature we use at 573 Kelvin. Okay, and around 35 atm pressure we will use. All the states in N-alkane will convert into its iso or a neo one. Okay, so for example, I'm writing CH3, CH2, CH2, CH3. This is called N-butane. N-butane, when heated at in the presence of AlCl3 or HCl at 573 Kelvin, what will happen? It will form a
Isobutane.
yes, this is isobutane. Got it? So this is a isomerization. Just nothing is happening over there. There is a shifting of bond only, or shifting of carbon only. Okay. One more example. Let's see. CH3, CH2, 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 CH3. Okay. Or CH2, CH3. AlCl3 with HCl at 573 Kelvin and 35 atm pressure. Okay, you have to tell the name. You have to tell the name of the compound. Okay, I'm making the compound. CH3CH, CH3, CH2, CH2, CH3. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yeah. One compound is this. What is the name of this compound?
2-methyl pentane.
Yes, it's 2-methyl pentane. Along with this, one more compound can be formed. It will be CH3, CH2, CH over CH3, then CH2, CH3. See, isomer, two isomers can be formed. What is the name of this compound? 3-methyl. 3-methyl pentane.
Pentane.
So this type of reaction is known as what? isomerization reaction. Okay. Next type. And the last one of chemical properties, that is pyrolysis. See, pyrolysis is, you can say, the decomposition of compound. The decomposition of compound by application of heat. When you are heating a compound and it decomposes into the further smaller compound, that is called pyrolysis. Okay, so in this compound we can take example of bigger molecule. For example, I'm taking C6H14. What is C6H14? Hexane. When I heat this compound at 773 Kelvin and 6 to 7 atm pressure, it will form C6H12 plus H2. This is hexene plus hydrogen gas. Plus, it can form C4H8 plus C2H6. Plus, it can form C3H6 plus C2H4 plus CH4. So these are the different combinations it can form on what? Pyrolysis. Okay. So just depending upon the amount of heat, or you can say product, or sorry, reactant, that what how bigger the molecule you are heating, the more different product will be formed. Okay. So this is a simple reaction. Just go through it once. Okay. Just give me 2 minutes. Yes. So we have discussed about the all chemical properties of the alkenes. Okay. Now let's discuss about the last thing in alkene, that is uses and stereoisomerism, or you can say conformations. We have already discussed this conformation and that purification, before that purification chapter, but still we'll do 2 to 3 conformations right now. Okay. So first, if I talk about the first uses, let's complete the uses. It's 2 to 3 uses are there. Okay. So generally methane is a form of a natural gas. Okay. So it is used for the running scooter, cars, buses. Also, LPG, if I talk about the LPG and all, that is also used as a fuel in homes, as a, you can say, for cooking. Okay. Second thing, if you want, if you know about the printing ink, that printing ink, it also contain the carbon black. It also contain the carbon black, which is also made from the methane. Paint industries, automobile industries, you can easily go through these. Okay, that's not a big deal. Catalytic oxidation of generally catalytic oxidation of alkane gives alcohol. Okay, so basically, just remember one more thing here. I'm telling you this today. This will help you till your 12th year or exam. Okay, alkane on oxidation gives out alcohol, while alcohol on oxidation, depending upon the condition, either it can give aldehyde or it can give ketone. Can give ketone, and when this ketone on oxidation gives out carboxylic acid, and carboxylic acid when oxidized, they gives out CO2 and H2. What you have to do, you have to just add the oxidizing agent. Okay, on reduction, it gives out carboxylic acid. On reduction gives out aldehyde or ketone. Aldehyde or ketone gives out alcohol on reduction. So this is a simple chart you can follow. So I said one use is very easy. Alkane is used to prepare the alcohols. Okay, to prepare the aldehyde, to prepare the carboxylic acid. Okay, generally, if I'll say a compound of methane, we have discussed, like chloroform, we have discussed CH2Cl2 dichloromethane. Okay, these are the compounds which are used in the laboratory also. As solvent, we are using the compounds. Some compounds you can say higher alkanes they are in the form of gasoline, kerosene oil, diesel, lubricating oil. Okay, so these are all also very useful. Okay, so let's discuss about the conformations. I don't think that the uses are that much important, but it was in the syllabus, so I just discussed it. Okay, you have to tell me, just because we have already discussed this, I'm making one structure only in the that is of I'll make of ethane. I'll make a conformation of ethane. Okay, first tell me which form is this. Which form is this? I'm giving you option: Fisher, Sawhorse, Newman. Yes. No one remember? Vignesh is there in the class. So this is Fisher projection. You all are not revising. It's confirmed now. Just because this was very small thing and we have done a full class on this only. Okay. See, this I'm making is called Sawhorse projection. Sawhorse projection, but how you remember this front? This is front carbon, this is back carbon, all the carbon is having, and if ethane, I'll talk CS3. This is ethane. Every carbon have three hydrogens, so I made three that's three hydrogen on each carbon. Sawhorse, but this form is called eclipse form. Okay, so what I will do, I will put the front carbon or the back carbon in the same position, and I will rotate the front carbon or the back carbon. Or means the carbon which is stationary will be same as it is. For example, this will be same, and I will rotate the back carbon. So this, when there is a rotation, just because around this single bond we have a free rotation. We don't have a restricted rotation. So this type of compound is known as was its staggered form. Staggered form. Okay. So this is eclipse. This is staggered. Okay. If I'll make a okay, this which type of third? See, I told you staggered. I told you eclipsed. I told you sawhorse, eclipse, and staggered. I told you Fisher also. Now I'm making the third conformation. Okay, just tell me which conformation is this. If you remember, probably if you haven't revised, it means you guys are not revising it. Okay. Yes. Which projection is this? Which projection is this? This is Newman. See, last time we have, when we were making the structure of cyclohexanes, we were making the structures of different compound having the halogens also, and that time we were replying that skew form is more stable or anti form is stable. So that time we were revising this because the topic was going on. Now, if the topic is completed and we are move ahead of that particular topic, it doesn't mean that you will not revise it again. Okay, and doesn't make sense of if I'll teach it further just because you are not revising the back classes. Just go through it once. At least give uh, 1 hour to a subject to at least revise the class and then go further deep in the class, like a book with the books. Just do the questions. Okay. So in the Newman, this is Newman projection, and same. Just because hydrogen is on the back side, so this form is known as eclipse form, and this is called staggered form. Okay, so here we have discussed all the things about the alkanes. Okay, so we don't have anything left in the alkane. Okay, let's start with alkenes. Let's start with the alkenes. Okay, what are alkenes? They are saturated or unsaturated?
Sir,
Unsaturated.
unsaturated.
Okay, alkenes are unsaturated hydrocarbons. Okay, containing the double bond. So let's talk about alkene. Alkenes are unsaturated hydrocarbon, general formula CnH2n. Then we'll say we have a double bond here. What else? We can say they are also known as olefins. Why olefins? There's a Greek word olefant, which means oil forming. Generally, they are oily in nature. That's why they are named as olefins. What else we can say? If I talk about the structure, we have one double bond. So carbon having 4 orbitals. So this is the px, this will be the py, and pz I'm making a small, one lobe small, one lobe larger. Again, second px, py, one lobe small, one lobe large. So see, this is a formation of sigma bond. One hydrogen will be there with a sigma bond, one hydrogen will be here with the sigma bond, and one hydrogen with this carbon with a sigma bond, one hydrogen with this carbon with a sigma bond. And see, this is side by side overlapping, and side by side overlapping lead to the formation of sigma or pi bond.
Pi bond.
Pi bond. So this is pi. So if you'll see, what is the structure of ethene? Ethene is this. Ethene is this. Two double bonds are present, and one is sigma bond, one is pi bond. So this is sigma bond, and this side by side overlapping lead to the formation of pi bond. We have two hydrogens here. So two hydrogen, one, two hydrogen on this side. So one, two. So this is the structure of a ethene. This is an orbital picture. You can say a orbital picture. This is the orbital picture of ethene. And you have to remember, see, I told you that simple thing that single bond contains the sigma bond, double bond contains the sigma, and pi bond, triple bond contains the sigma and 2 pi bond. Okay, so by this you can easily remember. So just make it like that only. Okay, so this was alkene, basic thing, unsaturation, double bond present, or that is oily nature, and sigma and pi bond. So this much is clear, I think. Let's discuss about the basic nomenclature, and then we'll move further to the isomerism, and then let's start with the preparation. Okay, nomenclature. We have already discussed the nomenclature. We were there for 10 to 15 classes. Okay, just tell me the name of the compound. I'm making the compound. You have to tell the name. Yes, first one. First compound name is?
Beauty 2 in.
Yes, very good. Second compound? Numbering should be done from the left side,
Two
right side.
comma three.
2, comma 3.
Two butene, sir. Two butene.
Dimethyl.
Dimethyl. Then but.
Beauty 2 in.
Okay, good. Okay, third one. So the main chain is 1, 2, 3, 4, 5. Why I'm doing numbering from the right side? Just because double bond is nearer. Okay, so you have to do numbering like this. Okay, I make 5 carbon. Yeah. Name. See on the second position,
3.
2. 3.
3 propyl.
No propyl. See how you'll do the naming of this. It will be 1, 2, and this will be considered the side chain in the side chain. So the name will be C 2, 4, 4 trimethyl. First we'll write the name of this, this, and this. Okay, so 2, 4, 4 trimethyl. Then on the third position, what is there? See how I will write the name of this compound. On the first position, methyl is there. So 1 methyl and 1, 2. That is ethyl.
Ethyl.
So this will be 3, 1 methyl
1
ethyl. Yes, 1 methyl ethyl. Then
but
pent, 5 carbon are there.
pent
Yes,
2 in.
yes,
Pent
pent
2.
2. Okay, I'll give you one more. One more of alkene. Okay, CH3, CH2, CH double bond, C single bond, CH3. We have here CH2, CH3. Yeah, name. Quite easy, huh? Yes, first one. First one, name.
2-ethyl
Then 2-ethyl then. Okay, I'm writing your name first. Okay. What is it? 2-ethyl
pent-2
pent-2-ene.
pent-2
How many are saying that this is correct? Okay, what is the first rule of IUPAC? To select the longest chain. See, if you'll go like this, 1, 2, 3, 4, 5, 6. Don't you think that you'll get 6 carbon in the main chain?
Yes, sir.
So this will be considered as wrong. So you can directly write 3 methyl. On the third position we have CS3.
Yes, sir.
6 carbon, then hex. Then on the third position we have double bond. Then 3-ene. See, this is the confusion. How the confusion creates just because you are not it's like you forget the first rule says that you have to select the longest chain. See, probably the straight chain doesn't mean that it is the longest chain. Okay, so let's answer the last one. Yes, name. Numbering should be done from the left side, right side. Just tell me this. See, from the right hand side, if I'll do CS3 is there. From the left side, if I'll do CS2, CS3 is there. The number of carbon is there, means molecular weight is there. So you'll do from the left side. 1, 2, 3, 4, 5, 6. See, on the third position, we have ethyl, 3-ethyl. Then on the fourth position, we have methyl.
4-methyl
We have 6 carbons, so it will be hex. On the
hex
third position,
3-ene.
yes, hex 3-ene. Okay, so just remember this thing. Okay, few points what you also have to remember, that is we have discussed the structure. This is structure. So about this structure, if I'll say some points you have to learn, the carbon hydrogen bond length. Carbon hydrogen bond length is around 1.34 angstrom. Carbon hydrogen, no, double bond, cannot on double bond. Okay, carbon hydrogen bond energy is equals to 143.1 kilocalorie per mole. Okay. Okay, the carbon present is sp2 hybridized. The carbon present is sp2 hybridized. Okay, there's three things. Just remember that this is important. Okay, let's discuss about the isomerism and alkene. We have already discussed. Just I'll give you the example. Okay, so you have to tell me the type of isomerism. I'm making the structure. Just tell me the type of isomerism. Okay, these are having the same molecular formula but different something different. There is a difference in something. Okay, just tell me which type of isomerism. Yes, speak fast. Say, don't you think this is a positional isomerism? What was position isomerism? When the molecular formula is same, but position of double bond, triple bond, or the functional group is different. So in both compound, carbon is 4, hydrogen is 2, 3, 4, 5, 6, 7, 8. Okay, and one multiple bond. So in the first compound, you will see this is but 1 ene and this is but 2 ene. So this only the position of double bond is different. So this is the positional isomerism. So this alkene generally show the positional isomerism as well as, okay, which type of isomerism? Okay, yes, which type of isomerism is this?
Geometrical.
Geometrical. First form is known as
Cis form.
and second one transform. See, if the same substance are coming on the side by side, this is known as cis form. If they are on the diagonal, they are known as transform. Just revise, but without revision, it cannot be possible. Okay, okay. Let's discuss about the physical properties. Not the physical property. We'll do directly to the preparation. Okay, then we'll go for the physical properties, chemical properties, and then let's change to the alkyne. Okay, so first is general preparation. General preparation of alkene. General method of preparation, you can say. Method of preparation of alkene. Okay, the first method I'm taking is dehydrohalogenation. Dehydrohalogenation, or you can say from alkyl halide or haloalkanes. So this is very easy. See, generally in this particular reaction, what exactly happens? The alkyl halide is heated with the strong bases. Okay, and strong bases you can take, you know, a KOH, NaOH, you can take anyone. Okay, and then the KOH is the base of the KOH is alcoholic, so we are taking an alcoholic KOH or alcoholic any base. Okay, then I go dehydrohalogenation. What is dehydro? Dehydro means removal of hydrogen, halogen, and also halogen. So dehydro, it means removal of hydrogen as well as the removal of halogen. So hydrogen, halogen, when both are moving from the compound, that reaction is called dehydrohalogenation. But what is the case? How it will remove? See, carbon, carbon. This is a simple alkene. We have halogen here, hydrogen, and rest are hydrogen. So this is functional group. This X. This carbon is called alpha carbon. This carbon is called beta carbon. Okay. This beta hydrogen will shift to this particular. This beta will remove and shift this bond in the mid, and this X will be removed in this way just because X is negative. Okay, so the compound form in the presence of KOH, or you can say alcoholic KOH, and on heating, it will form C double bond C along with HX. This H will react with X. So just because the hydrogen is eliminating from the beta carbon, just because the hydrogen is eliminating from the beta carbon, then we say it as this reaction is also known as beta elimination reaction. Known as what? Beta elimination reaction. Okay, so we'll discuss the reaction. We'll discuss the examples now. Then we'll see how the reaction is occurring. So first example I'm taking is CH3 CH2 I is reacting with KOH, alcoholic one, and the temperature I'm giving is 353 to 363 Kelvin. See what will happen. Now, this is X alpha, this is beta. Okay, for just remembering the reaction right now, what we'll do, see, the K will take the I from the alpha position. Dehalogenation is done. It will gives out Ki. It will gives out Ki. Dehalogenation is done. Now from the beta carbon, one hydrogen will react with this OH and form H2O. Now the beta, from the beta position, hydrogen is removed. So it means dehydrogenation is done. So this is called dehydrohalogenation. Along with it, you can see one valency of alpha carbon, one valency of beta carbon is there, empty. The valency is empty. So you can say it will form CH2 double bond CH2. So the ethene is formed. So we were preparing the alkene. The alkene is there. Okay, one more example you can see. You can tell me the answer. CH3, CH2, CH2, Br plus KOH, alcoholic. Temperature same, 350 through 363 Kelvin. Okay, what will be the product? Yes, product. K will take on the Br from the alpha carbon and OH will be take up hydrogen from the beta carbon. So tell me the product.
CH2 double bond, CH2 double bond, CH2.
How many double bond will be there? From only one carbon we are removing the hydrogen now. So one K will take on this Br, it will be minus KBr. One OH from the beta hydrogen. This is beta. Functional group first alpha, then beta. You have to just remove the hydrogen from the beta only. So this CH3 will remain as it is. CH3, CH double bond CH2. Okay. So one more thing. Okay, tell me the product of this. CH3, CH2, CH. Over it we have Br. Beside it we have CH3. Okay. In the presence of alcoholic KOH, you are heating it. Temperature will be same. Now tell me the product. See, if I'll say functional group first carbon is alpha, this is beta, this is also beta. So from which we will remove the hydrogen? See, both are. See, here we have one rule. That's why I'm teaching this example. Here both are beta hydrogen. Both are beta carbon containing beta hydrogens. So which will predominate? So the product can be two compound. It can be from the first carbon. So it will be, the product form will be CH3, CH2, CH double bond CH2. While if it's from the left beta carbon, it will be CH3, CH double bond CH single bond CH3. This product is 20% only and this is 80%. This is more stable. This is less stable. Why? There is a rule. The rule we say it as Setzef rule. Setzef rule. What this rule say? Setzef rule say whenever there are two alkenes, then the possibility of two alkenes, then the dehydrohalogenation takes place from the more substituent alkene. It means which already have more number of carbon beside it. So you can see this CH3 don't have carbon beside it, but this CH2 have this carbon. So this, if the carbon is present, so hydrogen will prefer to eliminate out from this left beta carbon. This is the Setzef rule. Okay, I'm writing the definition of Setzeff rule so that you can remember. You can write as well. What is Setzeff rule? According to this rule, whenever two alkenes are theoretically possible during dehydrohalogenation, then it is always more highly substituted alkene which predominate. It means those who is having more, or you can do one thing. You can use that carbon which have lesser number of hydrogen. See, left hand side we have 2 hydrogen, right hand side we have 3 hydrogen. So use it which have less hydrogen. So that will be more stable. Okay, getting my point what I want to say in Setzeff rule. The more alkylated alkene will be more stable. So the left beta carbon compound is more stable as compared to the right beta carbon elimination. Getting? Yes, clear or not?
Yes, sir.
Okay. One more thing you have to remember, the ease of hydrogenation, ease of dehydrohalogenation. Ease of dehydrogenation is iodides easily get replaced than bromides, then chlorides. Okay, just remember this. And if I talk about the alkene, 3 degrees more stable than 2 degree than 1 degree. Tertiary are most reactive compounds. Okay, so I think this is clear from the dehydrohalogenation. Any doubt in this? No? Okay. Second method of preparation is by partial reduction. By partial reduction of alkynes. This is very easy. What is reduction? A reduction is addition of hydrogen. So we'll add the hydrogen over here. Okay. So that is, for example, I'm taking CS3C double. Wait. That is CS3, C triple bond, C single bond, CS3. When it react with hydrogen in the presence of Na slash liquid NH3. We are taking liquid NH3. What will happen? One hydrogen will move to this carbon, one hydrogen will move to this carbon. And the compound form will be CH3CH double bond CH single bond CH3. See, from alkyne we are forming alkene. Okay, this is butene. This type of reduction in the presence of Na slash liquid NH3 is called Birch reduction. We say it as Birch reduction. Okay, clear? Sometime if someone asks that convert the cis-butene into the trans-butene, so you can use like CH3, C double bond, C single bond, CH3, H, H. Okay, so what you will do, you will use just leave this. We have one isomerism, then we'll do this. Or specific, you can do one thing also. Instead of this, I'll tell you one more thing. See, if this is trans-butene, then you are saying is Birch reduction. If you want to make cis-butene, you'll add Lindlar catalyst. You can use this. Okay, and what is the catalyst? H2 slash PD slash CaCO3 plus sulfur. So generally what happen? alkynes in the presence of alkyne react with the hydrogen in the presence of palladium, and that palladium is supported over the CaCO3, or instead of CaCO3 you can add BaSO4, and some amount of sulfur or quinoline is added, okay, to just stop the, you can say, reduction. Otherwise it will further reduce. So generally this much is sufficient for forming the cis alkene. You'll use Lindlar catalyst. For forming trans-alkene you will use Birch reduction, that is Na slash NH3, liquid NH3. So two type of compound can be formed. Clear? Just remember the catalyst. I'll forward this PDF also, so don't think you'll not get this. Third method of preparation. Third method is preparation is dehalogenation. Okay, now you have to remove only halogen. So generally we, in this type of process, we use vicinal dihalides. So you can write also from vicinal dihalides we can form easily. See, very easy method. CH2 1 Br with this, 1 Br with this. This is called 1,2 dibromo ethane, or you can say ethylene dibromide. This ethylene dibromide, when react with zinc in the presence of methanol, and when you heat it, okay, so what will happen? This zinc will take both Br and it gives out ZnBr2. Along with it, it will form CH2 double bond CH2, that is called ethene. So this method is very easy. Okay, so just because the halogen is removing from this compound, that is why we are saying it as dehalogenation. Okay, I'm giving you one example. Just tell me the product. See, this was okay. First, I'll give you the example of vicinal. I was making gem. First, give you the example of vicinal. CH3CH Br Br plus zinc. Okay, tell me the product. Tell me the product fast.
CH3 single bond CH double bond CH2.
Very good. CH3 single bond CH double bond CH2. Along with it will be have ZnBr2. Clear? So this is the
Yes.
formation of this alkene from the dehydrohalogenation reaction. Okay, sometime we were talking about the gem. See, when on different carbon is present, this is called vicinal dihalides. So if I talk about gem dihalide, gem means it means the Br are present on the same carbon. For example, CH3CH, we have here Br, we have here Br, and then we are reacting with the zinc in the presence of same CH3OH, and we are heating it. See, the compound will form the same. Zinc will react with both Br, it will form ZnBr2, and one of the hydrogen will shift from here to here. So it will form CH2 double bond CH2. So sometime it can happen that gem dihalide also undergo dehalogenation. That's not a big task. Clear this much?
Yes.
Yes. Okay. Let's do one more example. Tell me the product, and then we'll wind up the session. You can join next session. Yes. Yes, what is the product? See, just
CH
remove the. Yes.
single bond CH double bond CH
CH3 single bond CH double bond
CH2
CH2. Clear? Yes, correct. Plus ZnBr.
ZnBr.
Yes, clear. So, anyone else? Anything? Any doubt in this? Okay. So I'm just writing from the next class. We'll do the fourth method, that is from monohydric alcohol. From monohydric alcohol by acidic dehydration. So we have derivation of this. So on Sunday, I'll take the class, probably on this Sunday. Then we'll complete this particular alkene. Then only the alkyne will remain. So probably I'll take it to our class and I'll complete alkene full. Chemical properties, physical properties, preparation, and uses. Okay. So just revise this much at least. Okay. See you in the next class. Thank you so much.
Thank you, sir. Students, please join the next session.